All right, so we have 4 more problems to look at. I'd like to think that we can get all these done relatively efficiently. We should be getting pretty good at this stuff by now. Problems 9 and 10 are vertical motion problems. And the thing is with vertical motion, it's pretty simple. When an object is in free fall, and I described free fall in the notes, free fall is a pretty simple idea. It's just an object that is in the air, not touching anything, and it's not under its own power. It's at the mercy of gravity. And what do we know about gravity? Well, on the way up, gravity slows things down. On the way down, gravity speeds things up. Gravity causes things to speed up and slow down. So gravity causes acceleration. It causes objects to accelerate. So objects in free fall accelerate under the influence of gravity. Galileo, back around 1600, through some experimenting, figured out that the size of the object does not matter, assuming that we can ignore air resistance, which is simply the resistance that air has as an object moves through it. It has to push the air out of the way. And for small objects, especially for, not really small objects, but for compact objects that are moving relatively slowly, and I stress relatively slowly, we can ignore air resistance. So our air resistance is going to be minimal enough where we can get away with not dealing with it. The real reason that we don't deal with air resistance in these problems is because it's complicated. And so we like to keep things simple, and we just acknowledge that we are making an approximation by ignoring air resistance. But that's going to be a thing for the next several chapters. We are going to just sort of sweep air resistance under the rug and pretend it's not there. So mostly it's in an effort to keep things relatively simple. But what Galileo figured was, what he was able to show was that all objects accelerate at the same rate. And what is that rate? The acceleration due to gravity is, we use a little g. Little g is going to show up, oh my goodness, little g is going to show up in most of our chapters from here to the end, because gravity is ever present. And so it affects the motion of just about everything. So we give it its own special little letter because we like to abbreviate things. Little g is 9.80 meters per second squared. And what about the direction of that acceleration? Pretty simple. Gravity pulls things down. So when you are moving upward, gravity opposes your motion. When you're moving downward, gravity encourages your motion. But the direction of gravity is down. The direction of the acceleration that gravity causes is down. That is not inherently positive or negative. It is down, which means if you define up as positive, then the acceleration of gravity is negative. But if you define down as positive, then the acceleration of gravity is positive. So there's nothing inherently negative about gravity or its acceleration. It is down. Whether or not that is positive or negative depends on you. So, with that in mind, whenever you have a problem with an object that is in free fall, whether it's moving upward or downward or a little bit of each, if it is in the air and under the influence of gravity, you know what its acceleration is. And that's a key thing. Acceleration will be a given value. But they won't tell you that. You're expected to simply know that. Any object that is up in the air, you know its acceleration is g downward. So what do we have for problem 9? Problem 9 says we have a baseball that is hit upward. It's hit upward and it rises and rises. I'm going to get rid of this in the middle. Let's see. I'm going to move it over. So the baseball rises until it reaches its maximum height. And the problem says this. A baseball is hit, so it travels straight upward after being struck by the bat. A fan observes that it takes 2.8 seconds for the ball to reach its maximum height. Find the initial velocity and find its height. How do you do this? please, please, please do not go searching for some other way to do this. All of these problems are exactly the same. I just drew a picture. What's next? I need to define my axis. Instead of a horizontal axis, we now have vertical motion, but it's the same thing. Define where y equals 0 and define your positive direction. Please, y1 at the beginning of the motion. v1, right? And positive direction? Sure. I mean, by default, go ahead and make up positive. It's pretty simple. Make up positive unless there's a really good reason to make down positive. You got to have a good reason not to make up positive. And there are some problems. Some problems will have people dropping something. If you drop something and all the motion is downward, then it might make sense to call down positive because that's the direction everything is moving. Just throwing that out there. But unless there's a good reason, call up positive. Great. We got our axis, right? 0, positive direction. Where are the points of interest? The baseball starts down here and it goes upward to its maximum height. There's y2. I also need a v2. And then in between, I need acceleration and I need time. They give you the time is 2.8 seconds. What about the acceleration? The acceleration is negative g. What I would strongly recommend is do not write out this number. There's a reason that we have reserved g, because writing g is much, much simpler and will keep everything a little neater, much simpler than writing 9.80 meters per second squared. There is no reason to do this. Everybody knows g means the same thing as this. So the acceleration is negative g. That's all. It's just shorthand, much easier to look at. Also, it tells anybody looking at your work, oh, this thing's in the air. It's gravity. So the abbreviation serves all sorts of purposes. Use it. What about these others? v1. They're asking you to find the initial velocity of the ball. They're also asking you to find the maximum height. Find y2. What about v2? This is subtle. But if you are told an object in free fall reaches a maximum height, very simple principle. It went up, 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 and then of course it's going to come down. But as long as it is still moving upward, it has not reached its maximum height yet. It will reach its maximum height when it is finished moving upward, but in that instant that it has not quite yet started falling downward, which means it had a positive velocity and then a negative velocity. And what does the velocity have to be in between? When it finishes with its positive, but just before it goes negative, when it reaches maximum height, the vertical velocity is 0. That's a little sneaky, but it's a simple principle when you break down the logic. So by telling you that this is the point where it has reached its maximum height, they are telling you that v2 is 0. How many question marks do we see on the board? 2. How many equations are we going to write? 2. What do they look like? V final is v2 is 0 equals v1. Now, instead of plus AT, I'm going to insert minus g. I've told you, we do not put numbers in our equations, but that's another advantage to using g for this value. Remember, our equations are like sentences, and those sentences tell us the ideas that fit together, that describe what's going on. If I replace A with minus G, that sentence structure still holds. But now what I'm saying explicitly is, oh, this is an object that is in free fall and is accelerating under the influence of gravity. In other words, the meaning is still there. Anybody who looks at this stuff knows G means the acceleration caused by gravity, and so by using our minus G here, we are still preserving the meaning of this equation. And in fact, we're enhancing it by specifying that the acceleration is actually caused by gravity. We're going to do the same thing here. X final is y2, y1 is 0, v1 times t minus 1/2 gt squared. I replaced the a with a minus g. What do you notice about our unknowns? Where are the unknowns? The unknowns are v1 and what was our other one? Oh, y2. There you go, it's right there. What's our plan? This has one unknown. Get it, right? Simplest thing. After you get v1, get y2. Done. All right. That's it for number 9. Number 10 is also vertical motion. I'm going to leave that there. Leave this. Number 10 says, a student throws a set of keys vertically upward to her sorority sister who is in a window 4.3 meters above. The keys are caught 1.3 seconds later by the sister's outstretched hand. So, number 10, our picture looks like this. We've got a window here. We've got this girl is like hanging out the window. Building going through her head. She's like, throw me the keys. And then this girl down here is like, I will throw you the keys. All right, so we're going to go. The keys are going to be in her hand here. All right, keys are going to be launched upward. Like this. Right? That's the idea. Pictures. Oh, shoot. She needs a face. I'm sorry. She's like, catch the keys. Great. There's a picture. What do we need? Axis. We'll make positive direction up. Why not? And what are we going to do? How about y1 down here at the bottom? I'm sorry, 0 down here at the bottom. So there you go. The keys are going to start here. They're going to go up to her. What are they giving you? They're telling you that she is in the window 4.3 meters above. So where is y2? Let's go ahead and make y2 where she is. Yeah? They're going to go from here up to here. And what have they given you? T. Of course, the acceleration is minus g. The time is 1.3 seconds. Right? v1 is unknown. y2 is 4.3 meters. v2 is unknown. All of these problems are exactly the same. You should see that when you draw your picture and you lay out the information. If you have trouble seeing that, your picture is not done right. The whole point of this chapter is not to calculate answers, it's not to do physics. The point of this chapter is to demonstrate that all of these problems are exactly the same. Exactly the same process, exactly the same steps. Once you see that, and your brain then wraps around the idea of all the problems are exactly the same. This class, this chapter, this class, and your future of problem solving become much simpler. Can you write down the 2 equations? Yes. And then can you make a plan? And can you get v2 and v1? Yes. Now, they do ask you, what is the direction of v2? It says, what was the velocity of the keys just before they were caught? In other words, kind of like the car hitting the tree. What was the speed of the car just before it hit the tree? What's the speed of the keys just before they were caught, right? Find v2. They want the direction. What do you know about direction? If the keys are going upward, the velocity should be positive. A positive velocity means the keys are going upward. A negative velocity means the keys are going downward. When you calculate v2, it will either come out positive or negative. That sign of v2 tells you the direction. That's how it works. I'm going to go ahead and erase this and check my time. All right, we can keep going. Unfortunately, those were the only two vertical motion problems. And I say unfortunately because it'd be nice to have a few more, but then again, I mean, they're all the same, right? How many do we really need? We do have two more problems. We have the subway problem, Liz rushing to catch her subway, and then number 12 is Maggie and Judy running a 100-meter dash. So let's lay those out, see what we're going to do with them, and we'll wrap up chapter 2. Number 11, Liz rushes down onto a subway platform to find her train already departing. She stops and watches the cars go by. Now this is key. When she gets there, the train's already moving. Each car is 8.6 meters long. The first moves past her in 1.6 seconds, the second in 1.38 seconds. Find the acceleration of the train. And they specify it's constant, which of course, it's what we're dealing with, right? So, what do we need? A picture. What do we need a picture of? Let's go ahead and get your subway cars on there. Like this, this. And so the subway cars are each the same length, right? Let's go ahead and get Liz down there, right? We'll put her like here. She's like, oh no, ah. She's a little distressed, and that's all right, you know? It's one of those days. But what do they tell her? She gets here, and the first car goes past her in a certain amount of time that they give you. Then the second car goes past her in even less time, because of course the train is speeding up. Find the acceleration. How do we do this problem? You should know the answer to that. It is exactly the same as every other problem. There's your picture. What do we need? We need a 0 and we need a positive direction. Positive direction, no problem. How about to the right? Where's our 0? Well, to answer that question, we need to ask, how many objects are we keeping track of here? What is the object that is moving? It was really easy when there was a truck going that way. There was a boat going that way. There was a plane going that way. It's real easy when they just say, here's the object, tell me about it. Or here's some information about it. Now they're telling you the first car goes past her, the second car goes past her, but the two cars are linked together. So are they the same object or are they different objects? This can be a little bit confusing. And this is where sometimes you really have to put some thought into asking, what am I trying to find? What information are they giving me? And how do I organize it? So I'm going to give you the trick to this problem. There's only one object, the train. Okay? And what we want to consider is the front of the first car. Let's just consider the front of the train. And we want to track its motion. I am going to call this x1, v1. What is our next point of interest for the front of the train, the front of the first car? They tell you how much time it takes for the first car to pass Liz, which means in that time, that first car will go to right here. The front of the, when the first car passes her, the front of the first car is now over here. That is a point of interest. Nice. Then they tell you how long it takes the second car to pass. We're not interested really in the second car. We want to know about the first car. So in the next time, the front of the first car is now out here. So the points of interest are, after what times do they give us? They give us 1.6 and 1.38. The front of the car, front of the first car, the front of the train starts here. After 1.6 seconds, it is now here, 1 car length ahead. After another 1.38 seconds, it is now here, another car length ahead. And that's the key. We are going to track just the front of the train. What do we know about x2? It is 8.6 meters. What do we know about x3? It is 17.2 meters. What do we know about the speed of the train when it starts here? We don't know. Remember, when she got there, it was already moving. What do we know about V2? We don't know, right? We know it's faster. We don't know V3 either. What about here? Let's go ahead and put up A1, T1. And what do we know? We know T1 is 1.6 seconds, but we don't know A1. We don't know A2, but we do know T2, and that is 0.38 seconds. I'm just going to do this over here. And there you go. Every one of these problems is the same. We just have to lay out the information and then take a step back and look at it. And when we look, how many unknowns do we see? 1, 2, 3, 4, 5. How many equations will we need? We'll need 5. How many can we write? For the first interval, we can write 2 equations. Same thing we've been doing. For the second interval, we can write 2 equations. Again, same thing we've been doing. But we're going to need one more. And we've already dealt with this. We saw this happen with Speedy Sue. We can connect information in the picture. They ask you for the constant acceleration of the train. What does that tell you about A1 and A2? You should be able to make that connection. It's a simple connection, just like with Sue in the van when T1 equaled T2. Here, A1 equals A2. There's only one real acceleration. They're the same acceleration. We're still going to label them as A1 and A2 so that we have our information labeled properly. But in our equations, we're going to include A1 equals A2. There are 5 unknowns. We have one equation, we can write 2 more, and we can write 2 more. At that point, it's an algebra problem, and we'll make a plan. Let's see how it looks. So for the first interval, what are our equations for the first interval? V2 equals V1 plus A1 T1. I mean, same equations every time. What's the other equation look like? X2 equals V1 T1 plus 1/2 A1 T1 squared. What about for the second interval? We have V3 equals V2 plus A2 T2. And we have X3 equals X2 plus V2 T2 plus 1/2 A2 T2 squared. Okay. Whew. Now what do? Do not rush. Make a plan. I've warned you about this. V3 is the final velocity. How many places does V3 appear? Once. What do you do with this equation? From the start, you should be able to see that equation gets saved for later. Why? Because it is the only place where V3 appears. Your job just got so much easier. So now we just have 4 equations with 4 unknowns. What are the other 4 unknowns? V1, V2, A1, A2. And you can see A1, A2, V1, V2, V1, A1s, right? V2, A2. You can see they're all scattered among these equations. Let's go ahead and find those. Now wait a second. What do we already know about A1 and A2? What is our plan going to entail? Plan. Our unknowns are V1, V2, A1, A2. What are we going to do with A1, A2? We can already see this. Aren't we just going to replace A2 with A1 so that we only have just one acceleration? Let's go ahead and just call that, for simplicity, let's just call that A. Once we make that substitution, we're now down to 3 equations. We started with 5 equations, 5 unknowns, and just by looking at it, we haven't even done any algebra. Just looking at it, we've now reduced it to just these 3 equations. So let's go ahead and find our unknowns in those equations. We have A, and then we have, I hope the colors show up okay here. I'll try something like this. We have V2. Now, notice V2 is the final velocity for the first interval, but it's also the initial velocity for the second interval. This is why V3 only shows up in one place, but V2 shows up in a few places. So, notice V2 shows up in just 2 places. That's nice. And then what? I'll go ahead and use the red again. What's our last one? V1 is our last one, right? So V1, I'm going to do this. So we're saving this one for later, but looking at the 3 remaining equations, what do we notice? V2 appears in 2 places, V1 appears in 2 places. Yeah? That's kind of nice. So we want to keep A. We want to eliminate V2 and V1. If we are going to eliminate these by subbing, we simply need to decide which one do we want to eliminate first. We got to eliminate both of them, but we'd like to do things the easiest way first. Just looking at these, which of these is going to be easier to eliminate, V1 or V2? I'll tell you what I see. I see this equation is begging to be used for a substitution. This equation says, look, I'm right here. V2 equals this stuff, right? Don't even have to move it around. What if we just use this to sub V2 right here? So what if our plan is use the first equation to sub for V2 in the third equation? What will happen? If you sub this into here, this equation will now have V1 and A. This equation will have V1 and A. And you'll have 2 equations, 2 unknowns. We've already done this a few times. Done. And this is something else I'd like to drive home. We had a lot of problems in the beginning that were 2 equations, 2 unknowns. That's it. Now we've graduated to 5 equations, 5 unknowns. But if you take the time to simply make a plan and figure out what steps you're going to take, what you see is very quickly, through almost no effort at all, this reduces to, once again, 2 equations, 2 unknowns. So, make sure you take the time to think, make a plan before you start doing any kind of messy algebra. None of these problems require any complicated algebra. They do require that you make a plan and let your brain do the work for you. Can I put this into action? Yes. I am going to rewrite this equation. So I'm going to have x2 equals v1 t1 plus 1/2 a t1 squared. I just rewrote that one. And now I'm going to rewrite this one. It's going to be x3 equals x2 plus, I'm going to leave parentheses, t2 plus 1/2 a t2 squared. What goes in the parentheses? v1 plus a t1. Now, what's your next step? v1 is right here, and it's right here. A is here, here, here. We want to eliminate V1. To eliminate V1, you're going to have to rearrange one of these to read V1 equals and put it into the other. What I would recommend is rearrange this one to read V1 equals stuff. You're going to have to subtract this from both sides, divide by T1. Take the result, put it right there. At that point, you have one equation with only A. 3 steps more, and you're done. And that is how you handle Liz and her very bad day missing. It's not that big a deal, right? So she missed the subway. What happens like 5 minutes later? The next one comes along, right? It's really not nearly as bad as she'd lead you to believe. All right, let me get rid of that, and let's go ahead and talk about number 12. Maggie and Judy. Let me check my time. Ooh, let me check my battery too. Oh, battery's great. Okay, here we go. It's the last one. So what we have in number 12 is two runners. They have slightly different styles, and so they have slightly different timings and accelerations, but it says they set a world record in a 100-meter race. Maggie and Judy crossed the finish line in a dead heat. What does that mean? It's a very poor choice of words. But again, this is a situation where the author knows what they mean, right? Makes perfect sense to them. What does it mean by they crossed the finish line in a dead heat? It just means they tied. They tied. That's all. And so it means they both got to the finish line in a total of 11 seconds. Right? They both took 11 seconds to get there. Accelerating uniformly, Maggie took 2 seconds to reach her maximum speed. Judy took 2.8 seconds to reach her maximum speed. And then they each maintained their maximum speeds for the rest of the race. Now, I changed the wording a little bit because it is a little confusing, but it's important to note that they accelerated at different accelerations for different amounts of time, and they reached their own maximum speed, but they did not have the same maximum speed. So their motions were both different. The only thing they have in common is they both finished the race after exactly 11 seconds. So they asked, what was Maggie's acceleration? What was Maggie's maximum speed? And what was Judy's acceleration? What was Judy's maximum speed? And they say, what was their separation after 6 seconds? We're going to see how we're going to find all of these. So let's go ahead and just look at Maggie. Because we can find Maggie's acceleration, we can find Maggie's maximum speed, right? We can just consider Maggie's motion. So, she's ready to go. Her hair is already flying. She's like, yes, Judy, right? She's gonna have her, gotta have her Nikes on, right? She's ready to go. All right, there you go. There's my picture, right? Yours don't have to be this good. What do we do with this? How about we give ourselves an x equals 0? How about we give ourselves a positive direction, right? x1 equals 0, there you go. What do we know about her motion? Sorry, I'm trying to draw straight lines here. Well, she's going to start the race here. Points of interest. She is going to accelerate, right, until she reaches a point where she is at her maximum speed. And then she's going to maintain that maximum speed for the rest of the race. Where are the points of interest? x2 is where she reaches max speed. That is a point of interest. It's a point where something happens. And in fact, they tell you the time. The time here is, they tell you she takes 2 seconds, right? They don't tell you what V2 is. They don't tell you what X2 is. However, they do tell you what V1 is. It's the start of a race. So they don't tell you this explicitly, but what are you expected to be able to pick up on? She'd better be going 0 at the start of the race, right? Otherwise, boom, she's disqualified. There's no world record for her. Start of the race. Okay, she's sitting there, 0. What goes here? We don't know her acceleration. This is where she reaches maximum speed. We're not done with our points of interest yet, because now she travels constant speed. So now in here, she travels at constant speed until she gets to the end. And what is the end? The end is the end of the race. There you go. How fast is she going at the end of the race? Well, if she travels at constant speed, then it's the same as her max speed, right? Which means we still don't know. What do we know about V3 and V2 though? Well, we know they're going to be the same, right? Hold that thought. What goes in here? A2 and T2. What's A2? If she's traveling at constant speed, she's not speeding up, she's not slowing down. Constant speed means acceleration is 0. What about T2? Well, what you're told is her total time is 11 seconds. Be careful how you're given information. If this is 2 seconds and the total is 11 seconds, they essentially give you T2. But just be careful, it's not 11 seconds. What is it? Oh, it's 9 seconds. Take a moment to look at your information. We don't need equations right now. We need to look at the information and make sure that we have everything that we need. There are 2 intervals. What do we know? We're going to write 2 equations. We're going to write 2 equations. We're going to have 4 equations. How many question marks are there? There's 4 question marks. The problem is essentially done. Let's go ahead and write them down, see what it looks like. So let's go ahead and go for the first interval. First interval is what? V2 equals V1, which is 0, plus A1, T1. Nice. We got some zeros over there. That's going to make things real nice. What about here? X final, which is X2, is 0, right? X initial, 0. Nice. And 1/2 A1, T1 squared. How about for the second interval? We have V3 equals V2 plus 0. Now, a moment ago, didn't I just say, wait, V3 and V2 are the same, right? Well, we still have 4 question marks. Notice this equation, of course, came out V3 equals V2. Is it useful? Yes and no. We already established that we know these two are the same. But unlike before, where these were both known values, now they're both unknowns. So at least this is verifying, yes, V3 and V2 are both unknown. However, they are the same. And so this is a valid equation to include in our list because we have unknowns in it. However, it's a trivial equation. We're also going to find the only thing we can use this equation for is to get V3. It's the only place V3 will appear. But of course, V3 just equals V2. So yes, it is a valid equation, but it's trivial. What are we going to get then? X3 equals X2 plus V2T2 plus 0 because the acceleration is 0. So this one, I am going to put, we are going to save that for later because it's the only place where V3 appears. What are your other unknowns? The other unknowns are A1, X2, V2. Let's find them. Well, here's X2 right here. Here's V2 right here. And of course, here is A1. Now, notice all 3 of them appear in 2 places. V2 and A, X2 and A, X2 and V2. Like you got all 3 pairs. What do we need to do? We need to eliminate 2 and solve for a third. Now, you can go about this any way you like, but here is what I think the easiest way is. I think the easiest way is to eliminate V2 by subbing and eliminate X2 by subbing. Please, please, please don't make this more difficult than it needs to be. V2 is saying, please get rid of me. I'm just A times T. Put me right here. X2 is saying, hey, me too. I'm just 1/2 AT squared. Put me right here. If you just use these to sub out right here, what happens? You have 1/2 AT squared, right? T1 squared, and then you have an A T1 T2. Factor out the A and divide and you're done. If you take the time to just make a plan, what you see is, this is 2 steps of algebra and you're done. Solve for A. So you can then calculate A. Then, after you have A1, go ahead and calculate V2. And while you're at it, go ahead and calculate X2. What does the problem ask for? It asks for the acceleration and the maximum speed. Pop those in. Now let's talk about Judy. If we were to do this for Judy, what would we find? Judy's hair is a little bit shorter. It's just the way it is. Judy's time is a little different. Both times. But if we had to draw a picture of Judy, and if we had to define the axis, and if we had to define Judy's points of interest, what would you find? Her points of interest are exactly the same idea. This is where she reaches maximum speed. This is her maximum speed. This is her acceleration. In other words, if you were to go through this for Judy, it would be the exact same process, the exact same equations, the exact same algebraic result. You do not have to do it again, of course. If you already did this for Maggie, you can use the exact same result to calculate A1, V2, and X2 for Judy using her numbers. Maggie and Judy are identical, they simply have different numbers. So, we only need the one picture. And this is why we label this stuff the way we do, and this is why we do algebra, because now you can do it twice in the calculations. But the last problem they ask for is, who is ahead at the 6-second mark? So, to find who is ahead at the 6-second mark. This is why you need X2. For each runner, calculate X2. What do you know about X2? You know this is their position after this much time. So for example, for Judy, if it took her 2.8 seconds to get to her X2, then you want to know where is she 3.2 seconds later. So take the subtract T1 from 6 seconds. This is the time past X2. Right? You're following me. Good. What do we know about their motion past X2? They are running at constant speed. What is that constant speed? It is V2. So, multiply this time by V2. And what will that give you? That will give you their distance past X2 at the 6-second mark. I'm sorry, I'm running out of space. Follow the logic here. You know at this time they are at X2. You want to know where are they after 6 seconds. So determine how much more time they will be running. You know they're running at constant speed. The speed times that time gives you that distance. Now what do? Add that distance to X2, and you will then find where they are at, where Judy is at the 6-second mark. Do the same thing for Maggie. Using that simple logic, that simple process, you can find where each of them is at the 6-second mark. And if you know where Judy is and you know where Maggie is after 6 seconds, you can tell who is ahead and by how much. Any trouble with any of this, of course, as always, give me a holler. Written notes are also up there. Anything that I've said, anything I've drawn, anything that I've done, if it needs any clarification, send it my way. I'm always interested. And otherwise, let's put Chapter 2 to rest so we can move on to Chapter 3. Thanks for watching.